Hello everyone, and welcome to our video on vectors, the first data structure. So let's get right into it. The vector is a linear data structure that is very similar to an array. Should be thought of as a powerful array that has the ability to automatically resize itself when it's full. A vector can resize itself when it's full, which is ideal, which means there's no full capacity. So that's how it differs from an array. An array obviously can be full. A vector, on the other hand, it has the resizing capability, so it'll resize itself when it is full. It can access indexes directly, and that's known in the array, right? We can just do vector and then access whatever index you want, index 10, right? Put that in a cout statement or put it in like an if statement to compare it, or however you want to utilize it. But you can access indexes directly with a vector, just like you can in an array. You can add new items to the back of the vector. That is how you utilize the insert function, which is the pushback. And you can return the size of a vector, which is ideal because you can then utilize it for the for loop. When you have the for loop, for int I equals 0, I is less than my vector.size. So what it looks like, so you start off with a vector of size 1, and that's what happens when you create your vector right here. So of course you need to include the library, so that gives you the opportunity to utilize it in the standard library, standard template library, whichever terminology. So then we have our vector, which is created here, which then creates an integer of size 1. So that's what that picture is right there. That's our int array of size 1. And then user comes in and they do a pushback. Now we're going to do a lot of pushbacks, so let's do pushback 4. And then we repeat it again, pushback 5, pushback 6, pushback 7, pushback 8, and then, yeah, we'll leave it at that right now. So, saving space by just utilizing the little colons there. So, pushback 4, 5, 6, 7, 8. So let's walk through those one by one. First, we push back 4. Now, our size and our capacity equals the same thing. Our size equals 1, our capacity equals 1. When your size equals your capacity, you have to resize on your next input. So our next input, so we've completed this. Next input is a 5. So what do we have to do? Now that we know that we have an input and our size equals capacity, we create a new array, double the size, and yes, array is the correct term because the vector utilizes the array as its internals. It just adds functionality on top of it. So first we copy the value over, so that's a 4, and then we add our new value, which is a 5. So our size equals 2, our capacity equals 2. This gets erased. So now, again, and this has been completed. So puts us back in the same position where our size equals our capacity. So in our next input, we now have to take our capacity and double it again. So we take our capacity and we double it. Now we have an array of size 4. So first we copy the values over. So copy the values over, 1, 2, and then we add our new item, a 6, and now we update our size and our capacity. Our size is now 3, our capacity is now 4. And once you've copied the new items over, the old array is deleted. So now our capacity does not equal our size. So our next input, this input has been inputted, our next input can go in an O of 1 speed. So far, all of our inputs, because our size equaled capacity, made our input, so an insert equals O of n speed if the size equals the capacity. Otherwise, it's O of 1 insert. So this next insert, I can insert the 7 utilizing the pushback because there's an available position. Input the 7. That was an O of 1 operation. Our next operation, we now update our size equals our capacity. So our next input of the int value of 8. So the first thing we have to do is create a new array. Make it of size 8. First thing we do is we copy all the values over. We're copying the values over with a for loop, and the for loop's parameter is the size of capacity times 2. So that's why it's an O of n speed, because you can continuously do this resizing until it gets ridiculously high. When it resizes from 1 million, it's going to resize from 1 million to 2 million. After 2 million, it's going to resize from 2 million to 4 million. So the resizing can get very large, which is why the O of n is the speed for an insert, which requires the copying of all the values over. So every time you have to copy all the values over, that's an O of n operation. Every time that you have to just insert into a position that is available, then that would be a O of 1. So now all of our remaining inputs, which we'll create right now, so let's do input 11, pushback 12, and then pushback 13. So 11, there is an available position for 11, push back. Update our size, we should have updated our capacity already, but now we'll update size and capacity. Size is 5, capacity is 8, and we have just completed that input. Next, let's input 12, update our size, update our capacity. Our size is 6, and our capacity is 8. Oh, I'm sorry, I messed that up. Our size is 7, sorry. Size is 7, and our capacity is 8. Next, we are inputting the value of 13, and now our size equals our capacity, and that is our final input. That is taken care of. Now we have a popback function. So now we have myVector.popback. What it's going to do is it's going to pop the last item off of your vector. The last item on the vector is the value of 13. We're going to pop it off. Now, what you may think of when you hear pop off is that we're taking it and we are just literally cutting it off and dissecting it from the value. That is incorrect. All that means is that the next input is going to go into this location. So all it's really doing in the background is just changing the size to the value of 7. So that means the next input, so let's say right in here, there happens to be a myv.push_back 16. What all that means is that the 16 is going to come in and be inserted right here. And then our size, of course, will be updated to the value of 8. So that is how the popback works. It doesn't actually go in and delete anything. It doesn't come in and cut off the last item. It doesn't come in and erase the last item. All it really does is take our size, take the size, which was pointing to the value to our last index, and now it's saying that this is our total size, such that our next input goes into the last item. So that is how we push items back. That is how it resizes. And of course, now that it is full, the next time it resizes, it's going to resize to 16. So just thinking out loud here, let's talk about the numbers that it resizes at. It'll resize at 2. It'll resize at 4, 8, 16, 32. And of course, I'm getting these numbers because we're resizing and then taking this number and timesing it by 2, which is 4. Taking this number, timesing it by 2, which is 8. 8 times 2 is 16. 16 times 2 equals 32. 32 times 2 equals 64. 128. 256. 512. 1024. One thing we can also note is that this is 2 to the 10th, 2 to the 9th, 2 to the 8th, 2 to the 7th, 2 to the 6th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st, and you'll see how that comes around full circle, but these are all the numbers that it resizes. So anything that is 2 to the n requires a resizing. So it resizes a lot in the beginning and then it slows down. So for instance, out of the first 1,024 inputs, so 1,024 inputs, it has O of n speed and O of 1 speed. So it has O of n speed 10 times in the first 1,024 inputs, which means it has 1,014 inputs of O of 1 speed. So 10 times it has to do a for loop, copying over all the items to create a new one, and then 1,014 times it has the ability to do an O of 1 insert. Cool. That is how our vector works. So that's how we see that it is just like a souped up array. So now let's talk about speeds. The speed to access an item directly is O of 1 speed. Speed to insert is O of 1 amortized, and we're going to talk a little bit more about that. And the speed to delete is O of 1 speed, but that's just the Popback. And to search for an item in any linear data structure is O of n speed. So now let's talk a little bit more about O of 1 amortized. So just as we said before, in your first 1,024 inputs, you have 1,014 of O of 1, and you have 10 of O of n. Now, if you have 1 million, just about, give or take 1 million inputs, that, by the way, is equals, or roughly equals, 2 to the 20th, which means in the first 1 million inputs, you're going to have 20 inputs at the speed of O of n, and you're going to have 999,980 of O of 1. So if I'm inserting into a vector, and I have a total of 1 million inputs, 1 million inputs, in those 1 million inputs, I will have 20 inputs with a speed of O of n, and I will have 999,980 with a speed of O of 1. That is O of 1 amortized. That is called O of 1 amortized. Now, I know that when we talk big O notation, we always want to talk about worst case scenario. This is the exception. Reason being is 99% of the time, we are going to get a solution that is an O of 1 speed. And then 1% of the time, we are going to get a solution that is an O of n speed. So 99% of the time, we're going to receive O of 1, and that 1% of the time, which is even less than 1% of the time, as we're seeing right here, less than 1% of the time, you're going to receive an O of n speed. So that is O of 1 amortized. And that's what we see over here. O of 1 amortized means O of 1 on most cases, 99% of the time, and O of n on the edge cases being less than 1% of the time, and those are all the times that it requires a resizing. So I hope that makes sense on the vector, and we'll catch you over with our coding, and this is how we get some help if needed. So here in our code, we have first our libraries. We have the IOStream library and the vector library. We then have the using namespace standard. Here we have just a standard student class, super basic, private types, public types, just have a default constructor and a parameterized constructor. We then have a couple getters, so get name, get date of birth, get major, get campus-wide ID. And lastly, we just have the overloaded operator for the insertion. So I can print a student. Instead of having a print function, I can just use the insertion operator and print an entire object. So I will be utilizing this student object for all the data structure classes. So expect to see that for all the remainder. So now let's get into main. So I want to create two vectors, one of a primitive type, so string, and then one of a student type. So first the primitive type. So we have vector string, so creating a string vector of my vec. Then we have the vector size and capacity. So vector size is currently 0 and the capacity is 0. Now we are going to push back entry 0, push back entry 1, push back entry 2. Next, we have vector size. Now the vector size is going to equal 3, and the vector capacity is going to equal a total of 4 now. Then we want to do some access. So the way we access the item in index 1 is going to be entry 1, because index 0 is going to be entry 0, index 1 is 1, index 2 is entry 2. Reason being is everything is added to the back. So this is added to index 1, next item is pushed to index 1, next item is pushed to index 2, so on and so forth. So to see out my vec at index 1, it's going to print what's at index 1, which is entry 1. We're then going to print my vec.front. My vec.front is going to print what sits at index 0. So that's then going to print entry 0. Now let's do searching for a vector, searching for an item within a vector. So we're used to seeing the for loop of int I equals 0, I is less than my vec.size, and I++, but I want to show you a little bit different. Here's another for loop that is a loop that iterates through the myVec object utilizing the I. This is a little bit different. This is a range loop similar to how it's used in Python. So the way that I can access any string in here is just by utilizing the cout I. So I represents the string iterating through myVec. So if I, which is going to be entry 0, equals entry 0, then cout found, set the boolean to true, and then break out of the loop. So we're just displaying that we found I, so it's going to say found entry 0, and then it's going to break out of the loop. And because it is found, it is not going to display this. So that is how you search for an item. All of this if found is additional just to display back to the user that we found the item or we did not find the item. And then breaking out of the loop just makes it a little bit more optimized so it doesn't continue the for loop searching for an item that we've already found. But you just need a for loop to iterate through the item. That is how you search for an item. Lastly, we want to delete an item. So let's delete 3 items. So we do a popback, and a popback. Then let's check our size and our capacity. Now our total size is going to be 0, but our capacity is unchanged. So our capacity will remain the value of 4 as it was the whole time. Now let's get into a vector of a student object. So I create 5 students, A, B, C, D, E, and then I push back on all 5 students. So this goes, A goes into index 0, B goes into index 1, so on and so forth, all the way to where E goes into index 4. So we've added 5 student objects. What's the new size and what's the new capacity? So because we've added 5, our size is going to be 5 and our capacity is going to be 8. If our size was 4, then our capacity would have been 4. But because we added that next object, we then resized our capacity. So the way we access objects directly is you want to do cout and then object vec of whatever index. And of course, this is going to print the entire student object because this is a vector of student objects. So at index number 1, that is going to be the second item inputted, which is going to be object B. Object B is Jim Halpert. So it's going to print the Jim Halpert object. Next, let's go into searching. So we want to search for the student with the ID of the following. Does this student exist? So again, we set our boolean to false, and then we do the same thing. We iterate through our object. If I dot campus-wide ID, because I need to search by the campus-wide ID. So this is I is the object itself. I dot campus-wide ID returns the entire campus-wide ID of that object that we're referring to. So if the campus-wide ID equals what we're searching for, then we found, and then we're just going to say we found that person's name by their campus-wide ID. And then, of course, we set the boolean to true, and then we break out of the loop. Next, we are going to skip our if found because, of course, we found the item. Now, I want to show you 2 more ways that you can iterate through. Of course, I showed you this optimized way. We can do what we're always used to, being the int I equals 0. I is less than your object or your vector data structure dot size. so on and so forth. There's also one that we haven't gotten into yet, which we're going to cover in the next video, being the iterators. So you could use an iterator to iterate through your data structure. And then lastly is just the Popback, which pops an item off. So we're going to save it, run it, build it, and we're going to walk through all the prints. So back to the top of our int main. First we have the size capacity, and then 3 entries size capacity. So size capacity is 0, 0. Then we have 3 entries. Our size capacity is 3 and 4. Sweet. Then we have our item that sits at index 1, and then we have the front. Item that sits at index 1 is entry 1, and then front is entry 0. Then we are searching for the entry 0. Is it in the vector? And we found entry 0, so it does exist. Then we are deleting 3 items. What is the new size capacity? So we delete 3 items. The size is 0. The capacity is 4. Cool. Now we are in our student object. Added 5 student objects. What's the new size capacity? Our size is 5. Our capacity is 8. Accessing directly. So if I want to see out what sits in object 1, index 1, then it's going to print the entire Jim Halpert class. Sweet. Next, we are searching by the campus-wide ID of the following. Does the student exist? And we found Andy Bernard by the campus-wide ID. Lastly, we have the time complexity of the vector. So the average case and the worst case. The average case: access O of 1, search O of n, insert O of 1 amortize, delete O of 1. Worst case, the same for all of them except for insert, which is O of n. Of course, the worst case for the vector is that it has to resize, being an O of n operation, but the average case is O of 1 amortized. So these are really good numbers. If we were to look across the board, O of 1, O of n, O of 1 amortized, and O of 1, those are really good numbers. But keep in mind that you are trading these good numbers for potentially wasted space. So a vector's capacity could be anywhere from 50% full to 100% full. We know that for sure. We know that at worst case scenario, a vector will always be, if there are no deletions, worst case scenario will always be 50% full. Best case scenario, it'll be 100% full. So we have to keep that in mind as you're utilizing a vector, that you do get good numbers for your time, but you do have something called space, and you do have a little bit of wasted space. So potentially wasted space for good numbers. That's the trade-off for the vector. So this is an example of our vector. So this is, I want to specify the second one that we did, being that we added a bunch of students to a data structure, and then we searched for a student by their campus-wide ID, and we did that because that's a unique number. You know, whether you're a student, an employee, a citizen of the United States, whether that's your social security number or your driver's license ID by the state, or your campus-wide ID or your employee ID, you have something that's unique to you that is searchable. So utilizing the following, we have campus-wide IDs that we can search for these students. So this is a realistic approach of how you can store a data structure, or create the data structure, create the object, store it in your data structure, access in the data structure, search in that data structure, and then delete. So a walkthrough of how to use everything that you should be able to get through utilizing the vector data structure. So I hope this helped and made sense. Thank you.